Welcome, everyone. Great to see you all here. Thank you for coming. Fantastic to see so many people here in person, and welcome to everybody online as well. My name's Simon Thompson. I'm the Chief Executive here at the Geological Society. I'd like to start by thanking KSAT, otherwise known as Kongsberg Satellite Services, for sponsoring this event and indeed sponsoring our entire public lecture program throughout 2025. Among other things, it means we can be a little bit less austere than we have been, and we can even provide drinks after the lecture. On that, there are drinks in the lower library immediately after the lecture, and that will be through to last orders at 7:45. For an exit at 8 o'clock. A bit of housekeeping. We're not expecting a fire alarm. So if there is a fire alarm, it's for real, unless somebody's burnt the toast or something like that. We have fire exits, the two doors at the back. You can exit either via the main entrance or via the staff exit through the side of the lower library there, or you can. There's a fire exit just through this this curtain here that takes you straight out into the courtyard, and you convene just outside the Royal Astronomical Society in the courtyard. Hopefully that won't arise. There's going to be a Q&A at the end of the talk. If you are here in the room, just put your hand up and somebody will come round and give you a microphone to speak to. It is helpful to use the microphone so that the people online can hear you. If you're online, if you're one of the virtual attendees, just post your question in the Q&A box, and one of the staff here will read your questions out. So this is the inaugural presidential lecture by Professor John Goyas. John holds the chair in Geoenergy, Carbon Capture and Storage at Durham University. His research focuses on geothermal energy, carbon geostorage, natural hydrogen and helium exploration, and helium-induced seismicity. John formerly worked in the petroleum industry before going into academia, and he was the winner of the Geological Society's Aberconway Medal for Applied Geoscience. And he's had many honours and very distinguished positions, but I'm delighted to say that he is now the current president of the Geological Society. Welcome, John.
Thank you very much indeed, Simon, and indeed the Society. As Simon said, I've been around for a long time. And what I hope to do is skip through, I was going to say dance, but if I said dance, my wife would say, don't pretend, you can't do it. Anyway, I'd take us through some of the elements that I've been working on in terms of energy transition. Simon was kind enough to give some highlights from my CV. In a more straightforward way, I spent 28 years trying to get petroleum out of the ground as carbon, and the last 15 either not taking it out of the ground or trying to shove it back in again. A few years ago, I was asked to give a talk at the Durham City Trusts. Of course, Durham is famous for its coal mines, or was at one time, amongst other things. And it set me thinking, why did the Industrial Revolution begin? Why did it begin in the UK, and why really did it begin in the northeast of England? And diving into so what I'll do initially is look at how we got to where we are. One of the things that quite surprised me, it wasn't those top-hatted guys, the Isambard Kingdom Brunels and the Trevethicks and so on, who created the need for an industrial revolution, but the fact that we used all the firewood in England at least, and supply chains from Scotland or Scandinavia were not well developed in the 16th century, and basically we couldn't cook our food, or our ancestors couldn't cook the food. They were starving. So although coal had been known since at least Roman times and probably quite a bit earlier, it wasn't really the done thing to go underground where the devil was, but needs must, and we began to mine coal. And what was recognized, coal was the just revolutionized energy, if you will. You didn't have to grow it. You didn't have to dry it. Yes, dangerous, certainly incredibly dangerous going underground. But once you got that coal out, you got a lot of bang for your buck. A lot of energy in a small volume or a small mass of rock. And because in the northeast, at least, the rivers ran from west to east to the coast, it was actually a relatively simple matter to get that coal onto ships and down the east coast to London. Much easier than coal from the Midlands or South Wales or wherever it happened to be. That London became the first global city is down to the coal from the northeast. But it wasn't just London. Britain grew enormously. There's a correlation. The cause may be far more complex. Whatever the merits of having an empire, it was underpinned, I would say, by two things: abundant access to energy and probably Scottish missionaries as well. Now, we don't have to laud or support the emergence of an empire, but it was down to this accessible energy. And of course, once coal had been found, then we moved on to other fuels. And this just looks at the range of fuels which have been used through time. Up until really the early part of the 19th century, there wasn't much going on besides biomass. But what, of course, we've seen over the Industrial Revolution up until and including today is the massive use of coal and then oil and then that gas, which was often associated with the coal. And they're very energy dense. We'll show a slide in a few moments' time, which shows how much energy you get out of these systems. Now, there's something else which was going on at the same time as that increase in use of fossil fuels, and that's massive changes in the global population. I was born in the late 1950s when there were around about 3 billion people on the planet. A year or so back, something like that, is when we cracked through 8 billion. And we saw a change as well very recently. I'm perfectly on time. This slide's slightly out of date. India became the most populous country in the world, overtaking China. If we look at the bigger picture through time, going back even further to the mid part of the 19th century, we can see this almost exponential rise in the population. And if we combine the last couple of slides, actually that population has grown more or less in line with the change in energy. The separation at the bottom and nearness at the top indicates, broadly speaking, that we're using more energy per head now than we did 100 years ago, but they're in broad correlation. So a lot of the massive energy demand from the planet, or from humans on the planet, is due to the number of people. It's not all equally shared, of course. These delightful graphs, this is slightly out of date, but the picture wouldn't change appreciably. There are lots of folk do these on the internet, but the shape and the size, the area of the countries is, of course, proportional to energy consumption. And you can see what we already knew. Anybody in the room would say that there are a number of, let's call them gas guzzlers, whether it's in North America, Europe, and through more recently into particularly Southeast Asia. And that energy consumption is basically fossil fuels. And when you burn fossil fuels, of course, you get a greenhouse gas, carbon dioxide. And this is the equivalent picture for carbon dioxide. You've got a skinny South America, a skinny Africa, with the exception of a few countries in the north of Africa, and of course, Southern Africa. And then these behemoths of Europe, China, the USA, and more recently, India. It begs the question, how much carbon are we using? Now, what life has been very good at over the past 2 billion years or more is putting carbon into the ground. We're all carbon-based life forms, of course. I don't think there's anyone in the room is silicon-based, but who knows? There was once one on Star Trek, mended, I seem to remember mended with cement, which is not quite the right substance for, but anyway, here we go. There's only one piece of information on this rather complex chart I'd like you to take in. If you go through a wee bit of a calculation, you can come up with humans are using around about 100,000 years worth of stored carbon in terms of accumulated carbon in the earth every year. And I suppose that means a couple of things. Actually, given the length of time that carbon has been stored in the earth from ancient algae and so on, we've actually got a lot left in the ground, which I'll come to a little later on. But the rate is phenomenal. And of course, that's having a major impact on a number of things. The human population, I would say, is bursting at the seams at the moment. It'll likely roll over by the end of the century. But at the moment, we are impacting the biosphere with huge extinction rates. The geological record, of course, has gaps within it, but the best estimates are today extinction rate is about 10 to 100-fold what would be the normal pre-human background. The atmosphere, the greenhouse gas emissions clearly are changing the climate with temperature rise, unusual and severe weather patterns. But of course, most of that carbon dioxide, which is emitted from burning fossil fuels, ends up going into the oceans. And we're very close in some parts of the oceans now, which are slightly acidified by the CO2 to the point where skeletal carbon will be very difficult for the critters to precipitate. The Earth itself, the solid Earth, has much less impact, but who could have missed all the furor over the Blackpool earthquake caused by the one, or maybe one of two shale gas attempted wells in the UK a few years ago. So let's just look at how much energy we use. The International Energy Agency, based in the US, is a very good source of this information. And what used to be the BP annual review of global energy, now being looked after by the Energy Institute, are two really good sources of this kind of information. This is from the end of, this was published late last year and is current up to the end of 2023, and looks at the way in which energy demand in terms of exajoules are 10 to the 18 joules, pretty big. How that might change over the next few years to 2050, the date that many folk are targeting in terms of massive reduction in our emissions. And you'll see that there's a huge need to grow renewables and sustainable energy systems, whilst at the same time reducing or flatlining gas and reducing coal and oil, something we've been singularly useless at doing over the past 2 centuries or so, and in past 2 decades or so since the advent of the COP meetings. There are 3 bar charts or column charts on the right-hand side of that, and these, they've got different acronyms in the book, but basically the so-called steps is business as usual. The APE is meeting APS, it should read there. My apologies for my transposition error. APS is meeting commitments that were made at Kyoto and Paris and Glasgow and so on. And what we do to meet net zero by 2050. And I'll come on to define net zero in a minute. And what you see there, of course, is the complete absence of coal in the net zero 2050 scenario, and as things going, a failure to meet that. Where is the energy consumed? Well, again, taking data, there's a very good website called Our World in Data.organization. Incredible amount of information. You can plot these graphs yourself. You can see where most of the energy is used at the moment in the USA and China and India. The UK was in the top 10 or so 20 years ago of energy consumers. It's dropped out of that. We'll examine why that is a little later on. But what I'd like to do now is just change from looking at the total energy consumption to just what kind of energy is being used. And if you look at the top two countries there, in terms of use of energy per head, clearly very, very tiny nations. I think Iceland has got around about 250,000 people on it. Qatar, I don't know what the population of Qatar is. One is entirely underpinned by using fossil fuels. Iceland, not so. Obviously, geothermal plays a huge part in that. But you can see through the countries I've selected there just how different some of the nations are in terms of the brown is conventional fossil fuels, and there's a very sliver of mid-blue, which is the nuclear, and green, the renewables. Again, just repeating pictures of CO2 emissions that were shown earlier on in that rather distorted view, this time on a conventional Mercator map. Again, you can pick out nationwide where the big players are, China, the USA. It flips a bit differently if you look at it on a per head basis, with places like Saudi Arabia coming up very high, as well as North America, Russia, Australia, and certain parts of Europe. Let's just look briefly at the UK. And it looks, for the most part, well, there are two stories in the UK, I guess. Rather a lot of curves on this graph. I didn't choose the colors, I do apologize. But the palest one, the yellow, is in electricity supply, and carbon intensity is the y-axis. And what you can see with the dramatic fall off in carbon intensity in the last decade or so is the impact of removing coal from our energy systems. It's reduced the, we're heading very, we might just make in the next few years, I think it's 100 grams per kilowatt hour, or check my units there. We've done very well with that, but as far as the rest of the economy is concerned, it's pretty much flatlined. We've not really improved the performance of the housing stock. We've got plans, of course. They keep changing for the changeover in transportation systems, but those are in particular, the housing stock and the carbon intensity of heating are things which really need addressing. The UK has managed to reduce its carbon emissions quite dramatically over the last 20 years, in part because of the transition and the acceleration of coal out of our power generation system being replaced by largely offshore wind and more recently photovoltaics. But there's another reason, of course, which we should be aware of. And that's we've exported a great deal of our carbon footprint to places like China, who are doing the manufacturing that we once did. And so we shouldn't really be viewing all these, we shouldn't be, if you like, having bad players and good players. The world is very much connected. And so we need to look after the whole piece. So in terms of net zero and the just energy transition, what does it mean? The just piece has been inserted within the energy transition phrase to try and ensure that it's an equitable solution for all. If you remember a few slides ago when I showed those distorted pictures of energy consumption and CO2 footprint for different parts of the globe, what we must not do is disenfranchise, the less well-developed areas to simply satisfy our desire to reduce emissions. It's got to work for the whole planet. In terms of defining net zero, this often causes some confusion. The idea, as I'm sure most of you are aware, is to try and negate completely emissions of greenhouse gases into the atmosphere. That will be done by using less carbon-based fuels, but at the same time, there are opportunities for capturing some of those emissions in terms of carbon capture and storage, and there are lots of manipulations of this. We need to be quite careful, but offsetting those emissions by, for example, planting trees. But we mustn't forget the accounting systems are innately flawed. If I understand things correctly in these systems, you get to count a sapling, whether it lives or dies, as a fully mature tree. So don't let yourself get caught out by that. Let's flip back now very briefly to look at why it's so difficult, why we've got hooked, completely hooked on fossil fuels. And it's this energy density business. It's a lot easier to get your goods to market with a tuk-tuk and a litre of fuel than it is with a bag of carrots and the most willing donkey in the world. The energy density of carrots and donkeys is much, much lower than is packed into coal, petroleum, and petroleum-derived gases, methane, and so on. Way, way more energy dense are nuclear fuels. Few, of course, have got the opportunity to develop nuclear power, and it comes with its own waste problem. To date, I think only India has tried to develop thorium-based reactors, although there's 10 times more thorium in the Earth than there is uranium. The uranium system was originally developed because with the waste products from energy or electricity power production, you can make, of course, uranium bombs. The other element in the system that looks very promising indeed is hydrogen. Hydrogen is exceedingly energy dense, perhaps threefold that of petroleum gases, and it's part of the reason that you see hydrogen touted around by politicians as fuel of the future. It does have a couple of disadvantages, probably the largest one in many ways. Well, I'll come back to some of the issues on hydrogen in a minute, but it's actually low physical density. So although you get a lot of energy from a mole, a particular number of atoms of hydrogen when you combust it, when you have it as a gas, it's much lower concentration, as it were, in a volume than methane. So the doom, if you like, has been shown already in the last few minutes. Can we achieve net zero? There are some very clever people in the world who say yes. Clearly, even as I speak, things are going to get more difficult because certain administrations soon to be in place have a rather different worldview than perhaps mine is. But it will require a lot of cooperation in terms of policy, commitment from all of us, as well as governments and industry, and not least investment. And I'll finish the talk later on by talking a little bit about investment. So what are we talking about when it comes to renewables and sustainability? Renewables refers to at least in human timescales, that the energy source will not run out. And for that, we can think of wind. The wind will always blow. The sun, in broad terms, day on day, year on year, will continue to shine. They're also sustainable in that sense. And so wind, solar, photovoltaics, solar thermal, wave, tidal, biofuels, and hydropower are all fit into that category. I would say, although when I originally put this together, I would say geothermal, and I will show you why in a few slides' time, is also effectively, in human timescale, completely renewable as well. Clearly, we have taken a big bite out of the accessible uranium in the same way that we have taken a big bite of fossil fuels. So although it's rather questionable as to whether it's sustainable. There's also a lot of talk of the circular economy, and it's true that we can use materials and reuse materials, but when it comes to energy, entropy will increase with each use of energy. We end up being trapped by the second law of thermodynamics. But we can make better use of energy systems. A few years ago, one of the favored mantras from government, this probably about 10 years ago now, was we will take everybody's gas boiler out and give you all electric radiators. Now, I know the cost is just eye-watering. But to do that, ahead of decarbonising your power grid, is complete nonsense, because a power station is only about 50% efficient. So half of the chemical energy in the coal or the gas goes out the chimney as heat. In other words, had we taken that rather foolish policy through, then our carbon emissions would have doubled. So you need to think of the consequences. But how do we displace the fossil fuels? Well, the first piece is use less. And I guess if I had to repeat a word 3 times, rather than education, 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 when it comes to energy, mine would be insulate, insulate, insulate. If we used less and wasted less, we'd be in much better shape. But we need to add more wind generated electricity, and photovoltaics. In areas where we can deal with minimum environmental impact, we need to add where we can. Well, I think there's only one example of tidal systems that was operating in Northern Ireland, and that's now come to an end. We can harvest solar heat. There's a huge amount of wasted heat. The Earth is where I do my work, and geothermal, I'll illustrate in a minute, has enormous possibilities. And in a sense, heat for me is the real winner. If you use an electron to have the light shine, you've used it. But if you've got hot water, it might heat your house initially. But even when you've had the hot water and used it to heat your house, you could still use it to heat your greenhouse. So with heat, at least, we have this cascade system, and a rather more comprehensive picture is shown on the right-hand side there. You take heat out of your friendly volcano. It might be used for generation of power, and then a whole cascade of progressively lower and lower temperature enthalpy systems can allow you to keep extracting value from that heat down to just a few degrees above ambient. So heat's one area where we really don't optimize things. We need to be aware as well that the energy transition will require us to generate more electricity. This is a graphic from the aforesaid BP annual use of energy from a couple of years ago. They ceased doing it now. And it just shows really three curves. In order to meet net zero, they were forecasting we'd more or less need to triple power generation from 2010 to 2050. They had two other curves. They're quite derived, as it were. The new momentum is basically where the Earth's nations are heading, and clearly not generating enough usable electricity. Well, we're going to spend 2 or 3 minutes having a little bit of fun now, well, in a perverse way. You may recall we had several prime ministers one year. Was it 2022, I think? Shortly after the new PM came into place, these were the words which were linked to reducing our carbon footprint. We're going to use more coal, and we're going to install more, well, use more coal, gas and oil, and we're going to install more low carbon capacity. It was further unraveled or broken down into these topics. We're going to make more of North Sea reserves. Of course, we're 50 odd years into that. We'll have a scientific review of shale gas extraction again. We'll build 4 new clusters of carbon capture and storage facilities, and we'll reduce gas consumption. And that was the plan. And I've put in red beneath those my thoughts at the time from 2022. If we can use the North Sea reserves, and there are possibilities for using the tail end production in a much, anywhere between 0 and low carbon. We don't have any shale gas in the UK that we could extract. Just forget that one. CCS is important, but it's really quite minor. If we got 10 million years, for example, 10 million tons per annum from 4 facilities by 2030, our emissions in the UK are about 1 million tons of carbon dioxide a day. 10 doesn't take us very far. And yeah, it'd be great to reduce gas consumption, but they didn't say how. Now, whenever we do any of these things, whether it's the wind or the solar PV or the tidal energy, we have to watch its impact on biodiversity. Really, there's no free lunch here. There will be some impact from anything and everything we do. But we need to do those, we need to make those decisions before we launch into some grand program of developing tidal energy, for example, all around the UK. So let's look at some of those energy transition technologies and what we might be able to do with them. And I will concentrate on the ones I know about. So we'll start with geothermal. You know, it was on a trip a long time ago. It was a trip back to South America, where I did quite a lot of work in the 90s, to buy a slice of a field called Canyon Limon. And Canyon Limon was the biggest oil field in Colombia. I don't remember how much oil it was producing, but it was producing 1 million barrels a day of boiling water. And that's about 125,000 cubic meters of boiling water. And I said to my engineer, that's a lot of water. But before the days of Google, I calculated 1 cc is 4.18 joules. How much energy would you get from dropping that water from 100 degrees centigrade to ambient, about 30 degrees centigrade? And it was a very large number. And I said to the local engineer I was with, what can we do with all this energy? You can't do anything with low-grade heat, he said. And that was the end of it. But I hadn't forgotten that. And so when I moved from industry to academia, I started to look at it more carefully. The fact is, if you look at the energy calculations done by the British Geological Survey maybe 30 years ago, without putting cold water in the ground to warm up again, just simply abstracting it and adding up the basins and the various other hot granites and so on, there's about 100 years supply. If we take all the heating, if we're able to move all the heating over to use of geothermal. And when we add in what we might be able to store from solar thermal, or indeed waste heat from industry, it's even more. With that in mind, we started to think about, or a colleague started to think about, what might we be able to do with flooded, old, abandoned coal mines? There are 23,000 of them in the UK. And unsurprisingly, the heat demand from people in the UK sort of matches where the coal fields are. This is just for England, by the way. It does the same for Scotland. Surprise, surprise, we built our houses where we mined our coal. Indeed, there's only really one major population centre in the whole of the UK that isn't undermined, as it were, and that's London. And there's a lot of hot air in London. No, in the tube lines. And indeed, on the Northern Line, there's one scheme already extracting that horrendous heat you get in the summer, storing it and using it for space heating. So I'm not sure why you laughed, completely beyond me. More back down to earth, boom, boom. In the coal mine system, all those mines have been flooded after abandonment. The temperature of the water is anywhere between about 12 degrees, where it's at its shallowest, to coastal regions, say County Durham and Northumberland, where it may be 25 or 30 degrees, same in Staffordshire. We can circulate water through that system. And indeed, the first commercial one was Lanchester Wines, the biggest wine warehouse in the UK. Kind of neat that that's the first off the blocks, as it were. We're now modelling, and this is work from a colleague who started off life as a geoscientist studying subduction zones, and now he's looking at the heat transfer in mine systems. On the left is an old mine map, which we've digitized, and on the right-hand side is a model looking at re-injection of coal water in the bottom left, abstraction of slightly warm water in the top right. We are on production, not just at Lanchester Wines with about 5 megawatts. Gateshead became operational in 2022 as a whole bunch of customers, one of whom makes lubricants and is saying they can sell their products more easily because they can demonstrate how low carbon their processes are. Within this year, we should see 1,000 social houses at Seaham. Seaham is the area where Billy Elliot was filmed, basically, and the mines there have been pumping out water to maintain the level safely and avoid flooding of potable aquifers, and they've been pumping out about 4 megawatts. That will be used for social housing. Further afield, as far as me from the northeast is concerned, is some absolutely phenomenal work in both Eden and United Downs in Cornwall. I'm not quite sure, but United Downs should, within the next few weeks or so, see the first power generation of that's electricity from geothermal energy in the UK. But like I mentioned, we can gather waste heat from industry. This is a great piece of work done by a couple of engineering undergraduates a couple of years ago. And virtually all of the UK where we have people living has subsurface potential for storage, be it in flooded coal mines or in saline aquifers. And this is the work that was laughed at in Colombia, but applied to the North Sea. Many North Sea fields are running out of gas to drive turbines to put water in the ground and therefore get more oil out. Actually, the co-produced water you could use for power generation. For big fields like Ninian, maybe 40 megawatts. Not only would that reduce the carbon footprint of the fields, it would extend field life and because you're re-injecting cold water, you get better sweep efficiency. So there's lots of things you can do with geothermal. Let's move on to hydrogen, an area which I've been working in the last 5 years or so. At the moment, hydrogen is all manufactured. And most of it, virtually all of it, is used as a feedstock in the petrochemical industry. But if we're to start to develop a hydrogen economy, we will need a lot more. This is, I'm not sure even, just from a BP. I think this is also perhaps from a BP figure from a couple of years ago. We'll need it for power, we'll need it for transport, we'll need it for industry, or so it says. Now, some of you, many of you, may have come across the Technicolor dream coat that hydrogen now wears. There are different colors of hydrogen. I bet the hydrogen molecule never recognized that it came in different colors. Basically, hydrogen is manufactured, and it's manufactured by splitting methane or splitting water or a bit of both. And that influences what its carbon footprint is. And the ones that make the headlines at the moment are grey, basically produced from methane with no abatement of the CO2. It's actually worse than simply burning the CO2. Blue, where you use the same method for production but capture and bury the CO2. Green, where you electrolyze fresh water, and the planet's a bit short on fresh water. And you can see this is from a couple of years ago from KPMG, their estimates of cost per kilogram. On the right-hand side is their suggestion, I must inform you without any evidence whatsoever, that the cost of green hydrogen will drop to that which is grey hydrogen today. What if you get the Earth to do it for you? Natural hydrogen does occur. The well-known seepsit chimera or chimera, depending on how you pronounce it, in Turkey, contain hydrogen. There's bubbling hydrogen around the ophiolites in Oman. Has hydrogen been found in commercial quantities? Well, yes, it has. I can never pronounce this. Should we have a go? Bugu in Mali. Workers drilling for water in the 1980s struck gas. They then struck a match to find out what the gas was and unfortunately perished. It's 96% hydrogen. When your security detail is the Wagner Group or possibly its replacement, not a lot of information is forthcoming. But this Mali discovery is not anywhere that you would expect to find petroleum. It's in the middle of a continental mass. Broadly speaking, there are two really important mechanisms that produce hydrogen in the subsurface. The first and fast one, geologically, operating on the timescale 10 to 100 million years or so, is the water rock reaction, in which water with iron 2 bearing rock at temperatures of around about 300 degrees centigrade will react such that the iron will liberate or will take some of the oxygen from the water, liberating hydrogen, and go through the process of serpentinization. It's what happens at the mid-Atlantic ridge and places like that, although no hydrogen comes to surface because it's consumed by biological reactions. But elsewhere, such as in Mali, this process is producing molecular hydrogen. Similarly, the very same process that produces helium in the crust, the breakdown of uranium and thorium, the alpha, beta, and gamma particles, if they impinge upon a water molecule, they will split it. So there's and produce, the oxygen gets mopped up by the rock, the hydrogen gets liberated. So there's about half a dozen countries globally, companies globally searching now for hydrogen. Parts of Australia have already been licensed and drilling's been going on for the last 18 months or so. Let's turn now to the tidying up. The opportunity for capturing carbon and storing it safely in the subsurface was realized by the Hungarians in the 1950s, and more recently in the USA during the oil crisis of the mid-1970s. But in terms of putting together a program which would capture CO2 in the UK, we've been very, very slow. It's taken us, and I've been involved since this particular timeline started. Fortunately, with the advent of the COP26 in Glasgow, we eventually crossed the line, and we will see the first storage of carbon dioxide in the UK in 2 years' time. And we'll see it principally at 2 locations. In the Liverpool Bay Area, CO2 generated in the wake of hydrogen production will be stored in the old depleted gas fields offshore. And in the North Sea offshore, so Norfolk comes through here, there is a very large structure sitting between the gas fields called Endurance. That is a saline aquifer rather than a depleted gas field, and that will see injection of CO2 from Teesside and from Humberside again by 2027. In the last couple of slides, just very, very briefly, it's not all about energy itself per se. We need to think about the critical elements which will be required for that energy transition. And each year, the US and Europe at least put together a portfolio of elements which are endangered, as it were, because they're short in supply. And so it behoves us to use and reuse these elements and not send them to landfill. The other thing we need to think about as we're moving along is whatever we do, someone will object to it. And so we really do need to bring the public on side with the whole process. The energy transition to date has been somewhere distant. We switch our light switch and it still works. It will very much more come into the homes as time goes by. I'm just going to go and skip on to the very last slide. This is a summary of the last slide. Anyway, work by a number of different organizations, whether it's the International Energy Agency, McKinsey, or whoever, have demonstrated just what it will take in terms of commitment financially to make these transitions. And so in conclusion, it's critical that we decarbonize our energy systems for planet health and ultimately for human longevity. The density of fossil fuels is very difficult to crack. So doing what we've always done is really not an option. We have done a lot of the easy stuff, and now it will begin to impact people. And it needs to be for everyone, and it needs to be today. Thank you.
Thank you very much, John. Do we have any questions?
And start off with one from online. So Christopher Barry asks, do UK electricity emissions include imported biomass, often counted in the country where produced rather than burned?
Can you just repeat that for me, please, Alicia? Do UK electricity
emissions include imported biomass? Question mark, sorry. Often counted in the country where produced rather than burned.
I don't know properly, but I think not. You will see a promotional piece on a certain power generator's website, which says we're going carbon negative. So it's not just whether or not it's counted at the origin. Shipping is a grey area in terms of whether or not that's counted. And there's also this piece that the accountancy works on saplings planted, but with no recognition that some of those will die, many might die, or that they're not fully mature trees. So there's a time shift which is measured in decades anyway. And I don't properly know the answer to that question, but it's not, it's cheating, I think. But there we go. That's personal opinion.
Thank you so much.
Thank you, John. A question about geothermal energy in terms of actually extracting the stuff. I remember from stuff around Rosemanow's quarry about the amount of mineral that's dissolved in the water, and it precipitates out and blocks the pipes and blocks everything else. How are you dealing with that? How does that work in terms of mines?
I thought you were going somewhere else then. The production of scale and furring up of pipes is a very well known phenomenon from the petroleum industry. Particularly during late field life when entrained water comes along. So there are a variety of methods for suppressing that and keeping it in solution. One of the worst of all was the Miller field in the North Sea, which is full of barium. And when that came into contact with seawater, of course, you precipitated the completely insoluble barium sulfate. So there are a bunch of treatments. What I thought you were going to ask, which is the really exciting bit, is you spoke of Rosemanow's in Cornwall. The United Downs project has done a deal with Cornish Lithium using the new direct lithium extraction methods. Will start extracting lithium for battery production from the waters before returning them back into the ground. So it's not just lithium. There's been much less work done, but other important, not necessarily critical elements like zinc. So what else? There are several. Zinc comes to mind. There are several other metal species which sometimes occur in significant quantities within geothermal fluids. In Xi'an in China, the geothermal fluids are accompanied by exsolution of gas, which is rich in helium, and that's being extracted there as well. So it's not just solutes, but it could also be dissolved gases. Much more comfortable with that than trees.
Thank you very much. Is nuclear fusion a reality? I mean, is that going to take away a need for many of these renewables?
As a boy, I watched Tomorrow's World. Many hands up. Who watched Tomorrow's? Yeah. So Raymond Baxter, when he wasn't in women's clothing, and James Burke said in those 1970, I've got a school prize, which is the Tomorrow's World annual. I was reading it the other day on pollution, but I'll come back to that sometime in future. They said nuclear fusion is about 20 years away. When I arrived in Durham, I went to meet Damien Hampshire, the prof in physics who works on containment of fusion. I said, Damien, lovely to meet you. When will we have nuclear fusion powered stations? He said, about 20 years. And now I say that as a joke, but in fact, in the last couple of years, and someone here may know much better than I, the first fusion reaction has occurred in which more power has been generated than consumed. So we're actually getting pretty close. We will need, if we get to fusion, we will need a source of helium. So I'm playing my cards, you know, Simon introduced me, I'm playing my cards right on that one by finding helium without hydrocarbons. So it may be in our life, well, some are very much younger than you and I, but maybe in our lifetimes we might begin to see the first small demonstration fusion reactors, yes.
Great. Another question from online. Pete Webb asked, is it feasible to use methane by generating electricity at the gas field, export the electricity, then pump the CO2 straight back into the gas field? That would have the additional advantage of increasing the RF to near 100%.
Who's that from?
Pete Webb.
He's just read my bloody paper. That's I had published on that last year. I'm pleased to say it's just got the Paper of the Year award from Geoenergy. I think that is feasible, yes. What we now have in the southern North Sea is an array of depleted gas fields, some gas fields which are small and never been developed, and a whole array of power systems bringing the wind energy to shore. So the idea is that you would produce the gas, you would burn it in pure oxygen, which you can make offshore. That gives you pure carbon dioxide, which doesn't go through all that difficult process of capturing it because you've already captured it. The power generation would be used for making electricity. The concentrated CO2 could go back in the ground. Some work we did a decade ago has shown that CO2 will underrun the methane because although they're perfectly miscible, one is more dense than the other, and you get a pressure wave which will allow you to produce more gas. Actually, if you take that even further, in certain fields that are hot, over 100 degrees centigrade and have reasonable permeability, you could get to the position where you can set up a thermosiphon with dense phase CO2. It never emerges as a free gas in the air, and use that for power generation with what's known as a CO2 plume geothermal system. Works on paper. We haven't yet tried it in practice, but yes, I would do exactly that.
Thank you so much, John.
Killer question from Alison there.
This isn't going to be a killer question. I just wanted to know how worried we should be about critical minerals, especially for the solar and wind part of the transition.
Yeah, there are, and I guess you're referring to things like rare earth elements. If you've ever had one of those, well, I've got one on my blazer here with the JOLSOC badge, a snip at £4, I think. The magnets which are used for wind turbines contain the element neodymium, if I pronounce that correctly. You need about half a ton of neodymium for a 2 megawatt turbine. You need to mine 500,000 tons to get half a ton of neodymium, which is very environmentally destructive. And China, over the last 30 years, has acquired 96% of the global known resource. And so, and there are similar stories for a number of other elements. The concentration of lithium in what's known as the lithium triangle between Argentina, Bolivia, and Chile is also very environmentally challenging and limited to just those. There are supplies from rock from Australia, but is very limited. Helium-2, produced principally from 3 countries, the US, Qatar, and Algeria. So again, all of these are problematic, which is exactly why the US and Europe have published this, if you like, annual league table of critical minerals and how constrained they are. Having said that, a lot of people, you need to look for them. A few years ago, 2011, in trying to do a program on minimizing CO2 emissions from Jordanian oil shale, we couldn't get to Jordan. And so we looked at the oil shales which occur in the Lothians around Edinburgh. And if any of you have driven along the M8 and seen those beautiful red hills, they're the spoil tips of the old James Paraffin Young oil shale industry, and they contain ore grade rare earths. I valued the one outside Broxburn at £2 billion. We similarly found rare earths in soluble coal mine waste in Durham. So perhaps they're not quite as rare as the global market thinks. You just need to think laterally to look at, in particular, resource. We were looking at industrial waste streams. We even came up with an acronym for them: Geochemical Reclamation of Industrial Minerals and Elements, or GRIME for short.
I think we have time for one last question from online. Isaac Watkins asks, and bear with me, this is a bit of a long one. The areas you have highlighted for carbon capture and storage, North Sea, Irish Sea, north of Liverpool, also have many other uses: proposed wind farm development, marine aggregate extraction, established fishing industry, aquaculture, marine ecosystem wealth. What considerations would you highlight for the managing agents of the subsurface and land, terrestrial or otherwise, when assessing the subsurface land uses, especially alongside uses associated with decarbonisation activities?
Isaac, thank you very much. Well, I suppose there are sort of two answers in a way. The first, glib, but probably the most important bit, is that all of these potential users, and in the user piece, I include the natural world, need to be balanced. And so it can't be just one lobby system taking over. That said, there is a big difference between using or reusing the subsurface and reusing the surface. And so, for example, in Liverpool Bay, it won't result in new infrastructure. That infrastructure's already been there since 1996. It will be maintained at higher quality than would have been the case had it been abandoned. So your ABEX, your abandonment expenditure will be reduced because it's amortized through time. So I think that's a fairly positive outcome. Again, if you look to the southern North Sea, the huge amount of existing infrastructure that you could utilize should minimize the impact, the additional impact on the environment. But it's all going to be done collectively and in agreement.
Thank you, John. Thank you again to KSAT, our sponsors. Before we go and enjoy a drink in the lower library, just to mention, we really want you to come back on the 18th of February. That will be during Space Week, where we'll be talking about lunar exploration and in particular the Apollo and Artemis programs. But in the meantime, please join us in the lower library. That's just through these two doors here, for a drink and a chat. Cheers.
Thank you. I thought it was a bit incoherent. There we go.
It's great.
Glad you thought.